Hello everyone, it is such an honor to be here, and I will be telling you a little bit about all of what there is out there in the universe that we wouldn't know if we hadn't learned to look at the universe beyond our senses. You already had a little bit about who I am. I will just add one little caveat I've mentioned about my book. My book is technically, for now, being published by Unbound Boundless. Yes, I like the in the audience. Well, we don't know what's gonna go there, but I have bookmarks that you can come and collect. They're free later, and I can tell you all the gossip about publishing industry in this country. But apart from that, you're gonna have hopefully a good time as we learn so much about the universe. But I want to make clear that this is a tasting menu of talk. I'm not going to ask any question of you at the end. I don't want you to memorize everything that we're going to talk, because the goal of my talk is to make you realize just how extraordinary it is that we can understand the universe thanks to ingenuity, because we have been moving beyond what we can perceive of the universe. So just enjoy the ride. And the first step in our journey through the universe is not too far from here, is the largest moon of Saturn, Titan, because we're going to look for our first invisible rainbow. So that is Titan as seen in roughly humanized colors. And it is an exciting world, very, very exciting world, but as you can tell there, it's quite boring. It's just an orange ball, and just like, okay, Alfredo, sell us that this is an exciting world. That is the only world in the solar system, apart from Earth, to have rivers, lakes, seas, and rain. And the rain is going to be the important thing. But it is not, those lakes and seas and rivers are not made of water. They're made of methane and other hydrocarbons, because Titan is extremely, extremely cold. And the rain is a crucial part, because methane is also transparent like water. So light passing through it would form a rainbow. And you might be thinking like, but it's orange. What kind of light is passing through it? And you're absolutely right. No visible light is passing through it. But when the Cassini mission went and looked at Titan in infrared, saw this. Now, I know it's quite bright, but, can I work the laser? Yes, I can work the laser. Yes, I can work the laser. There, that dot there is sunlight reflecting on an alien lake. And it is incredible that we build a machine that can travel 1.5 billion kilometers to look at sunlight reflected on an alien lake. And we know that rain is quite rare on Titan, but there's been recent observation from JWST that actually saw clouds lifting from the lower layers of the atmosphere to the higher layers of the atmosphere, showing that there was rain. So there is rain, it's transparent, and most likely there's going to be a rainbow. But it's going to be in infrared, so we wouldn't be able to see it, even if we could stand on Titan with our own 2 feet. And this was the idea of invisible rainbows. There is so much that we can do in astronomy thanks to the wavelength beyond the visible. And we're going to explore all of them and some of the cool things that we discover. But it's also a very political book. We heard a fantastic comment earlier about how everything that we do is political. And as a queer person, as an immigrant, my life is not just political, it's also politicized. So I wanted to bring a very, very obvious parallel. When Trump got power, the first few things that he did was banning well, getting out of the World Health Organization, stepping out of the Paris Agreement, and defining, well, to be honest, that was absolutely so unscientific beyond everything, defining that everyone's sex begin at conception, which technically made every single person in American female. But let's go, girls. But that's the problem when authoritarians don't see just science as something evil. And I have this parallel, and on one side is the first book burning, 6th of May, 1933. And most of those books are from the Institute of Sexology, where the crucial earliest scientific analysis of being LGBTQ done by queer people themselves, because we shouldn't have, it's nothing about ourselves without ourselves, were burned because they were considered Jewish science. But there were also other books there that were considered Jewish science, and among them there was Einstein's theory of general relativity. And the connection will be obvious in a second, because the other photographs is from May 4th, 1933, 2 days apart, and is the announcement by Carl Janksi of having discovered a weird radio signal from the depth of space. For the last year and a bit at the time, Janksi has been working in the Bell Laboratory, and he kept seeing the signal repeating every 23 minutes, 56 seconds. So at first I was like, it's close enough to a day, right? 23 hours, 56 minutes. Pretty close to a day. Maybe something sun-related, maybe something else. And then I realized that sun takes exactly 24 hours. 23 hours and 56 minutes is the time that the Earth rotates with respect to certain stars. And what it was seeing was the signal of something at the center of our galaxy. And what it actually saw could only be explained with the theory of general relativity. And on one side of the Atlantic, they were burning Einstein's book, and the other side, that signal was played. It's just a hiss. It's not really anything fancy. It's just shh. But they were playing it on the radio because it was like a big discovery. And what we have the technology now to do is to actually see that signal. And we go into the radio waves and we meet our supermassive black holes. So the images seem, when they were first published, we're seeing the shadow of the supermassive black holes. Sagittarius A star is the friendly neighborhood, the supermassive black holes at the center of our galaxy. No, it's not going to eat us at any point in the future. And luckily, it's chill, so it's not going to blast us with a beam of radiation like M87 star, which is at the center of an elliptical galaxy and has a jet of material that stretches for millions of light years. Sagittarius A star is very chill, active in a very tiny way. And thanks to radio wave, we can see the ultimate region around it, the event horizon. And when the pictures were published, they're like, aren't they a bit out of focus? Fair. It's the fact that we don't have the technology yet to see better than that. But I need you to understand how revolutionary they are, because the only way to get that image was to synchronize a radio telescope from the Greenland all the way to South Pole, from Europe to South America, from Africa to Hawaii, all together working at the millisecond to act like a single instrument, so that we could see something 26,000 light years away. And it would be equivalent to see, with your naked eye, a donut on the moon. And I think, even if you weren't see the donut in perfect focus, you would think it's pretty impressive. And thanks to that, we can test that lots of astrophysics, a lot of expectation about what black holes are, and also relativity. And for as much as we want to believe that we know that there is more than just general relativity, and we know there's more than quantum mechanics. It's just that we don't know how to find what's there. And we would like to find, oh, we got there and we find something that is wrong. Haha, that's our path forward. No, Einstein is right on everything there, so we'll find it somewhere. We're going to move slightly off the supermassive black holes, but we're just going to stay at the center of the Milky Way, because there is one thing, the radio waves, that do so well, and it's one of my favorite fun facts, and is discovering what kind of molecules are in the gas clouds that are all over space. And this one is Sagittarius B2. Sagittarius so tells you they're in the neighborhood, and has ethyl formate. And you were like, okay, who cares about ethyl formate? I don't know. And it is important because it's a precursor of amino acid. Amino acid makes protein, and so it's very important on life on Earth. But I can bet you have definitely smelled it and most probably tasted it. Ethyl formate is mostly the smell of rum and half of the taste of raspberry. So I make a really good cocktail based on that cloud. What you can do, it's incredible. It's a gas cloud 26,000 light years away, and you know what kind of molecules there are. I cannot tell you that the cloud tastes like rum, smells like rum and tastes like raspberry, because mostly the main component is cyanide. But I don't do the cocktail with cyanide, but is the fact that we can learn those kind of things thanks to radio waves, something that we wouldn't know if we were just studying the universe with visible light. And another exciting thing is seeing beyond, even in our own neighborhood. This is the highest precision image of the moon, and it was done with radar. Using just radio waves, sending them up and getting back down, and allows to see a few meters under the surface of the moon. And if any space agency actually will get us back to the moon in the next few years, this is going to be very important to find ice deposits and ways to have maybe a settlement on the moon. This approach is also used to predict asteroids. You can predict the position of an asteroid up to 10 centimeters, which is amazing. It just takes a while because there are not many radio observatories that can do this kind of radar. And my favorite things about the radar, they turn Venus in a disco ball. You're thinking like, okay, why are we giving scientists money if you're just doing silly things? There is a scientific reason. We didn't know we didn't know how long Venus took to spin. Venus spins very slowly. A day on Venus is roughly 243 days on Earth. So very slowly. So what they thought is like, what if we send radio waves to Venus? Because Venus has a very thick atmosphere, so you need the radio waves to pass through it, bounce off the ground, and come back. And like a disco ball, just measuring how long it took for this rotation and based on sending radio waves and back. And the final thing that I will mention about radio waves is finding impossible objects. So, last year, researchers found a galaxy with no stars, which you might argue, and we're getting into the philosophical here, is a galaxy with no stars a galaxy? Like, that seems like a pretty simple requirement. A galaxy is a collection of stars that somewhere in space. Yeah. So it's a big gas cloud, a big hydrogen cloud, as large as our galaxy, so 100 light years across. But as far as they can tell, there are no stars. They tried to look with Hubble, they couldn't find any stars there. So who knows? But also they found it by accident. They literally put the telescope in the wrong position and found a signal. And they're like, what is this? Apparently, galaxies. So, and the standard things is when you think there could be something out there, even if you have zero evidence, you might have an example. If you definitely have one example of something, you definitely have a population. So you cannot find something randomly in space and think this is the only unique object. So there's probably a lot more out there that we didn't know, and literally we only discover in 2024. Now, we move on to microwaves. And the microwaves, our focus is obviously the cosmic microwave background. That is the fossilized echo of the Big Bang, the first light that shined through the universe, once the universe was cool enough for light to travel freely. And what is extraordinary of this is a map of just the light that was emitted, but also a map of how the universe eventually will become. Because what we're seeing here, it's a temperature map, because it's easier for astronomers to think of it in terms of temperature. The bluest blue, which are the coldest, and the reddest red, which are the hottest, are just 1 of 10,000 of a degree centigrade apart. This tells us that the universe on large scale is roughly all the same, which is incredibly important because it tells us that the properties that we see in the universe here, all are physical, or the science that we think it works here on Earth, we don't know if it works on Andromeda. We don't know if it works at the furthest reach of the universe. This map telling us that the universe that we can see is roughly all the same. It's tell us that our science, what works here, probably works on the other edge of the universe. Absolutely fundamental. But just to mention a few other things the microwaves can help us do is we can look at the birth of planets. This is a protoplanetary disk where 2 planets, probably more, are being born. And what's exciting is this we've never seen anywhere else, is you have a nice little planet here, big planets, probably a few times the mass of Jupiter, but there is a second planet forming on the same orbit. We don't have something like that in the solar system, but maybe it's possible. We think it was gravity would make things too unstable, but we found one example, so there might be more out there. And the other thing that we can do is we've seen the birth of star system. We can also look at microwaves at the end of stars. And one of the things that I really like is the fact that you have supernovae. We're going to talk more when we get to the energy part, a more energetic part of the spectrum. You have massive release of energy, a lot of light, but then all that material that is being thrown out cools down. You still want to study it. How does it evolve? Because, and we'll discuss more later, we humans, we come and we are formed from this supernova. All the materials that make us come from this stellar explosion. So you want to understand, once they cool down, how it happens. And then we move on to infrared light. This is a beautiful image from JWST in which we're seeing a stellar nursery where the stars are being born. Those clouds that are formed and are polluted by material from supernovae are just organized in these massive clouds, and we see this star inside being born inside this massive cloud. And it's wonderful. This is this kind of observation. They're brand new, only a few years old, are helping us understand where those star systems come from, how the solar system was born. And we also are looking further than ever before. This is one of JWST Deep Field. And this image alone, I know it's very bright, but it contains 45,000 galaxies. Hundreds of them, when the image was released, never been seen before. And it's just like, this is a tiny fraction of the sky, and it is filled with other galaxies, some as big as ours, some tiny, and is helping us understand how these galaxies change over the ages of the universe. But I want to mention 2 really fun facts about infrared astronomy. One is the lowest, deepest node in the universe. This is the Perseus cluster. You can see Hubble in the bluish, and that is a Spitzer image. And what you can see here is big waves of gas going around. That is a supermassive black hole, not as calm as ours, one that is very active, that is spinning, and creating these ripples every 9.6 million years. And everything that repeats in physics is a harmonic, a musical note. And in fact, that is a B flat. 57 octaves below middle C. There is a supermassive black hole at the center of a massive galaxy, not far enough, but not too far from the Milky Way, and it's creating a musical note. And it's incredible that we can connect something, the physics of harmonics is actually something that's been established for centuries, to something that is so new that we only know existed thanks to infrared astronomy. And to truly bring the point home, it was another discovery that is extremely recent about just how little we understand of the universe. So we think that planets form around stars, and anything that forms like a star is a stellar object, and that forms from collapsing material into something very dense and then starts shining, or not start shining that much. Instead, planets form from pebbles, and they build up, and they become bigger. And then we found these jumbos, Jupiter mass binary objects. It's possible for planets to be thrown out of their star system. We have found rogue planets or free-floating planets around the Milky Way. Not a problem. But we assume that you couldn't form something as small as Jupiter just by making it collapse. That's not anything in our physics that tells us that we could do that. And then in the Orion Nebula, they found multiple binary objects roughly the mass of Jupiter. They cannot be planets because you cannot kick two planets out and get them to spin together. At least maybe you can get it once, but not multiple times. But also our physics doesn't tell us that we cannot create planetary objects just from collapsing. So I interviewed a researcher in my day job and asked, so what do you think is going on? And he literally said, I have no idea. I hope that some theoretician can come up with something because they don't make sense. So brand new stuff that we can find out when we're looking at the universe beyond the visible light. Now we step over visible light and we move into ultraviolet. Ultraviolet is unfortunately the sort of the black sheep of astronomy beyond the visible, because it's very difficult to do it from the ground. Well, it's impossible to do from the ground for a good reason. The ozone layer, we don't want to die of radiation, so it's good that we have the ozone layer. But nobody wants to send us stuff that do a lot of UV lights because, if it's very energetic, we can probably get it on something with X-rays. And if something that has a lot of UV light but is far away, we're going to get in on the infrared. So we're happy. So there's not much on UV light, but I think there are some very fundamental things that it's important to know. First of all, why would we study the universe, especially local universe, in UV light is because young stars are full of UV light. So we want to see those stars. We want to understand how again, the Milky Way has evolved over time. And this is the Andromeda Galaxy, which is the largest, nearest galaxy to us. And we want to have those kind of pieces of information. But closer to us, and a lot more important, we want to understand how our sun works. And one of the crucial things is to look at the sun in ultraviolet. If you were lucky enough last May to see the aurora shining over the UK, we knew that was coming because we could study the sun in ultraviolet and in X-ray. We're going to get to the X-ray in a minute. And it's something that helps us prepare for our technology and just our day-to-day life. And the sun is a good star, but it gets active and creates problems. The aurora are very pretty, but the activity of the sun can damage satellite technology and more, and so we need to keep an eye on it. And talking about the aurora, a lot of places in the solar system have weird aurora. And most of them are in ultraviolet. They're found in all gas giants, they're found in some comets, and what you see here, which is just a very weird aurora, happening on Mars. And I found aurora on Mars first in ultraviolet, and only last month we found it in visible light as well, which is very exciting for a planet that doesn't have a magnetic field. And now we get into X-rays. This is the beautiful Whirlpool galaxy, and everything that you see there in bright and purple, which, okay, the middle bits of the two galaxies, it's a galaxy merger, and everything else, it's either a black hole, a supermassive black hole, or some very extreme event of some sort. And when it comes to high energy light, X-rays and gamma rays, there is a challenge. Capturing that light is very difficult. It's very difficult to send it to a device that can say, hey, there was a few photons there, oh, there's this. I mentioned in the JWST on infrared that that image alone had 45,000 galaxies. Of all the entire sky, we only know of 900,000 unique X-ray sources. Everything else is lost in the crowd. And 710,000 sources are supermassive black holes in other galaxies. Said, ours is pretty chill, doesn't do X-rays or anything. Well, does a little bit, but not in any dangerous way. Not that you can see from millions or billions of light years away. And 180,000 X-ray emitting stars come from the Milky Way. You know, it's like, stars, we're looking at the sun in ultraviolet a minute ago. There's more to the sun. Well, what's more to the sun is a big mystery, because it's the corona, the atmosphere of the sun. We've seen the surface of the sun. It's hot. It's in the 5,000, around 5,000 to 6,000 degree, depending on where you're looking. But the corona that we can see during a solar eclipse is the atmosphere. And for some reason, which we've now started to understand, is about 2 million degrees. And you're like, but the heat source downstairs, literally down, is cooler. How can you get something 200 times hotter? And we think there is a weird play between pretty much the sun's surface is not heating up the corona, and at least not directly. It's the magnetic field of the sun that is very powerful and changes, it flips every 22 years, that is creating that. There are also other sources the last little bit of sources in X-rays are some of the most extreme objects in the universe, and they are neutron stars. So when stars go supernova, and to go supernova, a star needs to be a little bit more massive than the sun, at least 8 times, sometimes a lot more. This is what happens. The layers of the supernova collapse first because there's nothing powering it inside, and as it collapses, it explodes. What happens is the core is compressed to something that it's extreme, that we really need to get into quantum mechanics level there. And it can generate something that are unique, because suddenly all the properties of the star are compressed and release a lot of energy, including X-rays. And to understand this object, this extreme powerful object, it's impossible without having the X-rays that provide this understanding. And neutron stars were discovered actually first as pulsars with radio waves by Dame Jocelyn Bell Burnell, and we didn't know that they existed before they were discovered in radio waves. And it's something that it's whenever we look at the history of light beyond the visible, it's like this over and over again. We are at the last type of wavelength, and I will quickly go to our most existential part. So gamma rays, this is the gamma ray sky. As you can see, the sources are smaller and smaller. There's fewer and fewer, actually. Mostly we see the plane of the Milky Way, where a lot of the sources get overlapped. But we can only find 7,000 known sources of gamma rays. It's just because it's so difficult to get such energetic light. And it's what's interesting also is that we have several gamma rays observatory in space and gamma rays events can outshine all of the universe sometimes in a matter of seconds. And we're going to discuss those events, and don't freak out until the end. I know there's going to be something that it's a bit spooky. But first of all, the important thing, the reason why you have an appetite, or the reason if you have gold jewelry on you is because of the collision between neutron stars that I mentioned, and they create this short gamma ray bursts. They are releases of gamma ray light that last at most 2 seconds. And those are the, in those collisions, everything that is quite heavy elements, including platinum, including gold, including iodine that regulates our thyroids, is formed there. We cannot just have the supernova that form the neutron stars for us to be us today. You also need to have a collision between 2 neutron stars for those elements to spread and to be created and spread and pollute all of the universe. So supernovas and collision between neutron stars are crucial for who we are today. But they are also pretty terrifying. So this is a long gamma ray burst. So this is created by a massive star going supernova. And this is the most powerful that is, it's called BOAT because it stands for brightest of all time. Astronomers love an acronym. And what I'm showing you here, it's what the signal looked like, but what and it just speed up. I think it lasted, if I remember correctly, it was just over 10 minutes. But it did something to our planet atmosphere. It made it ring the ionosphere, the part where it's full of electrically charged elements, ring for about 8 hours. So there is a supernova exploding in a completely different galaxy, 2 billion light years away, and this light traveling all the way to Earth and making our atmosphere shake. And it's just like, ooh, and I know your next question is like, so would something happen closer to down there, okay. Closer to us, well, no, luckily. We have the closest star to us that can go supernova is Betelgeuse. It's not going supernova anytime soon, unfortunately, because I really want to see a supernova. Come on, Kepler and Tycho Brahe had 2 in the space of 20 years. I feel that is a bit hogging in the supernova. But even if they were to explode, Betelgeuse is not massive enough to create something like this. But the fact that something like this can affect our planet, I feel that gives us this cosmic connection that, yes, we are on a tiny speck of silicon orbiting an ordinary yellow sun, but we are connected to the wider universe. And this is the whole universe beyond our senses. It's only started in the 60s that we start using telescopic instruments to look at the universe beyond our senses. But I feel, and I hope I have demonstrated over the last 7 decades, that we have massively expanded our understanding of the universe. A lot of things that you might have heard of, they were discovered thanks to light beyond the visible. And light is not the end. We are very much at the beginning of a new revolution in astronomy. It's called multi-messenger astronomy. We're using gravitational waves and neutrinos to understand even more of the universe. And I think it's absolutely fantastic that we are right here, right now, in this absolutely special moment for astronomy. And with that, thank you very much.
Thank you, Alfredo. What a cool, colourful and exciting field to work in. You certainly brought that to life. It was fabulous. So we'll have some of your questions and short, pithy statements with question marks at the end of them. We'll go for the further galaxies from the start. So if we have someone, the lady in the orange cardigan.
Hello. Alfredo and I actually met at a Star Trek convention. So, my question is not going to be, do we believe in life on other planets? But it's going to be, when will us humans meet aliens?
Oh, good question. You see, part of the radio chapter is all about talking to people at SETI. And I can tell you that now in South Africa and Australia, and the collaboration is based here, Jodrell Bank in the UK, we're building the most advanced radio telescope ever. It's called the Square Kilometre Array. And is the fact that when we think of science fiction, we think a very purposely sent out message. We're going to receive something. If there is an alien civilization within 10 light years, which you might think, oh, it's not that much, but there are plenty of stars. If there is an alien civilization within 10 light years that have a square kilometer array, just like we're going to have in a year and a bit, they will be able to detect the pings of our cell phone towers. So aliens might be listening to our conversation soon, just like the British media. We are constantly leaking radio waves out into space. So I think that it might be well possible that somebody has already listened to us. Are we going to meet them? It's more complicated because, well, as far as we can tell, we cannot build a warp drive. I wish we could travel the stars, but we can not. But I think discovering alien life, even if it was simple life forms on one of the moon of Saturn or Jupiter, or finding evidence of ancient life on Mars, I think that would be a very important, fundamental discovery, but also will, I think that's, to be very specific on the humanist side, I think we are uniquely prepared to not just be like, oh yes, did Jesus appear to the aliens as well? Are we the chosen people? I think our approach to seeing we are part of a greater universe, of a natural universe, I think put us in a position that we're like, yes, let's engage with this monumental discovery.
Lovely, thank you. Any questions from this end? This gentleman here.
Will it ever be possible, or is it possible now, to focus gravitational waves and neutrinos in anything like the way we can the other wavelengths?
You have the finger on the pulse. There's just been a paper, I think, published either yesterday or 2 days ago about gravitational lensing of gravitational waves and neutrinos. And it's, at the moment, we do not have the technology. Neutrinos are particles that are so light that for decades we assumed that had no mass. If you hold up your, I don't know where the sun is, but if you hold up your thumb towards the sun through your thumbnail, there is about 100 billion neutrinos passing every second. But you're like, okay, I don't feel anything. I don't think this is a very fun demonstration, Alfredo. But that's the point, is the fact that they're constantly streaming through the planet. And to detect them, we have massive detector. One is Ice Cube in Antarctica. So they use about 1 kilometer cube of ice and just cameras. And with the expectation that eventually one neutrino from something in space will hit a molecule of water in the ice, create a flash of light, you photograph that, you can work out what it is. And at the moment, we do not have ways. Like, I can think of a few sci-fi ways to make that possible, but if there would be ever possible, or if they could be something in the next few decades or the next few centuries, I cannot tell.
Lovely. Anyone in the back have a question?
Firstly, can I just relate to the first question? Who says we haven't been visited by aliens? I've met some strange people over the 72 years I've been in this life. This question's coming completely out of left field. I'm a historian, military historian. I concentrate on the Second World War. I was just wondering if you have any thoughts on the scientific progress that was made during the Second World War. How does it actually... I mean, I've read books from the 60s that say it was a huge advancement. I'm just wondering if current scientists think the Second World War produced a huge advancement in what allowed you to get into what you're doing today.
Yeah, I think that is a whole other talk, but thank you for the question. I think the crucial thing is, unfortunately, a lot of the time we are not critical enough of science and how science is created and for what reason. And I think often enough we like to believe that, we like the fairy tales that scientists are progressive, scientists are always objective and factual, but we are humans, we have biases, we have agendas. We can discuss how the space program probably wouldn't have happened without the Nazi scientists, and this is a fact. We cannot pretend that oh, no, things would have been different. No, that. But we can also consider that there were plenty of scientists that refused to collaborate. It's complex, and I think we need that kind of complex discussion. We need to have we so often, and so I think is partially is human nature, partially is social media that has brought us to be succinct and specific and take a very strong position on everything. But we need to discuss how the world is complex. That I talk about politics of space quite a fair bit, and yes, it's terrible that pretty much billionaires can do whatever they want in space. But at the same time, the solution is not oh, we shouldn't send stuff to space. No, our day-to-day life depends on space, from your GPS to predicting weather, and not just oh, it's gonna rain today. It's also long-term prediction about crops and everything. Fire monitoring from space. We unfortunately are linked to space. The fact that billionaires can do whatever they want is because there is lack of regulation, and that is a political issue. So when we look at things historically, we need to see that, yes, a lot of the things that we benefit now have a terrible history, but we need to put it into context. Actually, sorry, I know I'm going on many tangents, but there is one perfect example. There is this thing called the Haber process. You might not have heard it, but is the reason why we can produce enough nitrates to fertilize, and technically we could feed everyone on the planet, then we can get into capitalism later. But the Haber process is fundamental, it's incredible, and probably saved billions of lives. But it was created by Fritz Haber to create mustard gas. So, kill millions. Fritz Haber, clearly terrible human being. And yet, that same process now help us feed billions. So it's things are complicated. We cannot, literally, we cannot not share the grayscales. We cannot say everything is black and white.
Brilliant. Thank you so much. Thank you for all your great, thank you once again to Alfredo.